today we will be discussing in brief the role of anchor nodes in network evolution. So actually we will be briefing how a network will gradually get evolved when additional links are being added over the time. And in this particular discussion, we'll be talking about evolution of a linear networks. So why linear network, that we'll be discussing later in the presentation. And then we'll be identifying the anchor nodes through analytical derivation. So what is anchor node and how we have found anchor node in a string topology, that will be following all the corresponding slides. Then we'll be giving an example of application where anchor nodes are used to create an efficient heuristic design to add links. And also we'll be discussing why this heuristic design is required in such real-world application scenarios. And at last, we'll be showing a few open research issues which involves the application or the identification of anchor nodes. So let us start with the first one, the evolution of linear networks through link addition. So before going to this particular link addition techniques and how it has been evolved, let us see what do we mean by anchor nodes. So if you will give a simple Google search, that anchor node in communication networks or networking, whatever, not only anchor nodes, then it will give some different answers. So the first answer that I got from Google search, so which tells us what the anchor node is the leader of the group. And the group may have a tree structure with the leader as the root to optimize for communication. So with this answer, we can have a few phrases that we can pick up. The first one is the leader of the group. The second phrase is tree structure. And the third one is the optimize for communication. So actually anchor node involves in these three particular areas. So if you'll see, so anchor node actually will reduce the end-to-end distance between a distant source and destination over a large size network. So that's why it is telling that it is optimized for communication, and that is the primary advantage of identifying an anchor node. Also, anchor nodes improves communication reliability and robustness. Why? Because the anchor node, if you have multiple links attached to an anchor node, obviously you will have multiple paths to reach a distant node. So as a result of that, the robustness of the network will be enhanced, because if one of the links will not be utilized, we'll have other routes to reach a distant node. And that also makes sure the communication reliability. Also, the anchor node can act as hub nodes. So this is called this leader of the group. So where we can see hub nodes, mostly if you will go to any like computer lab, you will get multiple network switches where all those optical cables are being connected. All Ethernet cable are going through a particular switch. Also, we can see web servers and internet gateways. So like, for example, IIST has its own internet gateways. So all the communication through the internet is coming through a particular IP address. So that is the gateway. So that is working as a hub node for the entire entity of IIST. So this is becoming the leader of the group. So the internet gateway can be the leader of the entire group of IIST. And this formation of anchor node can be found naturally or artificially. So whatever until now we have seen this network switch, web server, internet gateways, those are artificially made. So we know that where to place a gateway. We know where to place a web server like Google web server. There are only few Google web server across the globe. Then we know in a particular like network setting where to place the switch. But also we can see in many cases where the anchor nodes are gradually getting evolved. Like for example, social network. If you'll see any network like Facebook or maybe such kind of LinkedIn. So if you'll find some key person in that particular network, say for example, if you have a Facebook account, you may have a few of your friends in your friend list who will have many friends in their friend list. So if you have a friend to that particular list, you can directly communicate to the other friends who are the friends of your friend. So if you will see LinkedIn, you can see there will be like first, second, we can see in the like suggestion list in a LinkedIn. So like when it is like second, third, that means like you are only 2 hop away from that particular person. You are maybe 3 hop away from a particular person. So for example, if you have a friend in your LinkedIn network and who is maybe the director of an organization, of an institute, you will find many others who will be maybe like in 2 hop, you can directly reach to them. So those are like naturally evolved anchor nodes in a network. So the question is like, what is this reason behind such emergence of anchor nodes? When we are making it artificially, obviously we have seen it naturally, it is being evolved and we have mimicked that particular idea in an artificial setting, like where we are creating one like network and we are creating some network switches and others. But what is the reason? So in this particular discussion, we'll be like discussing how this emergence has happened. So until now, if you have any question, please ask. Any question? Okay. So for this particular study, we have some preliminary assumptions that for this particular study, in today's discussion, we have taken a string topology network. So here we have given an example of 40 node string topology network. So why we have taken string topology networks? The main reason is one of the sparse networks existing in the real world. Because if you can see in this particular string topology, if one of the links is not working, there will be island of multiple networks. And we can find this kind of string topology networks in many real world examples, like community broadband network, then highway communication networks, then disaster response scenario, then in many real world military communication networks. Now in IoT, then IoT and M2M setting, even like industry 4.0, there also you can find multiple string topology. Now you may ask why there is no string topology, there will be multiple nodes, but mostly if you'll see those network is very sparse. And if you have a bird eye view, you can see maybe that network is nothing but a tree topology. So the tree topology can easily be mimicked as multiple string connected together. And in this particular thing, we will try to identify how a string topology is gradually getting evolved by addition of long range link or LLs. So what we mean by long range link? So we'll add a link between two nodes which are not directly connected. So for example, in this particular figure, if you'll see, we'll not add any node between any link between node 1 and node 2 because it is already connected. But we may add a link between node 1 and node 11 because it is not directly connected. So long range link means which is it will be connected between two nodes which is not already been connected. Otherwise, it will be a parallel link. And for this particular study, we did not consider parallel edges and self loops. So this long link can be added based on two strategies, either based on random decision making or maybe based on greedy decision. So when we are taking it as greedy decision, what we are trying to do, we are trying to optimize one or multiple network characteristics of a network. So for this study, we have taken average path length as the characteristics which we will be greedily optimizing for the rest of our discussion, whatever results or graphs will be showing, everything will be implemented just to optimize the average path length of a network. So here we have given a simple example that how to calculate average path length, which actually estimates end-to-end path distance among all nodes average over the network. So here when I am telling this path distance, if it is a unit link network, so it will be like hop distance. So if the distance between two consecutive nodes is always unity, then like path distance and hop distance are same. And in rest of the examples, wherever we will be showing, all will be unit distance link. If it is not, then we will be mention it explicitly. So in this particular equation, you can see the graph APL, the APL of G is nothing but all the distance between all the nodes. So here Dij is nothing but the cost of all the to reach all the nodes. So here that's why we have given Cij. C means cost of Ij. So here cost is nothing but how many hops you are actually traversing. So here if you will see the matrix, cost matrix, you will see that if you will see the first row of the cost matrix, it is from node V1, how many hops are required to reach all other nodes. So obviously from V1 to V1, it is nothing is required. That's why it is 0 and all diagonal elements are 0 because as we are not considering any self loop. So if you are in V1 or V2 or V3, you don't require any hop to reach V1. You are already there. So from V1 to V2, it is directly connected. That's why it is 1. V1 to V3, you can reach in here in 3 ways, either V1 via V2 to V3 or V1 to V5 to V3 or V1 to V4 to V3. These three the three paths are equal because here we have assumed that all the links are unity distance. So if there will be weight, then you need to calculate the distance. You need to add those weights and see the least distance between the node, and that will be the cost of reaching V3 from V1. Similarly, for V4, it is directly connected. V5, it is directly connected, and V6, there exists only one path, that is V1 to V2 to V6. It is the shortest path we are taking. So if we will take everything and we will add, then it will become almost like 1.33 hops to reach any node from any other node in this particular network. So here we have shown for this APL that we have taken all the nodes. Now, for example, for this particular case, you can see this matrix. You can take the upper triangle or the lower triangle of this matrix, and it is like similar, right? It is not different because you are going to V1 to V2 and V2 to V1. Still, you are taking only one unit, not otherwise. So in that case, this APL equation will become n into n minus 1 by 2 if you will take either upper triangle or lower triangle matrix. Any question until now?
Hello, sir.
Hello, sir. Hello. Hello,
Okay.
sir. Can you hear me?
Yeah, please, please.
Sir, how are you telling like real world networks or string topology majorly? Like,
I
they
am
are
not
always
saying that real world networks are all are string topology. That's why you can see here. I have given a few examples. Not all the topologies are string, right? So just take
even
like a highway communication network. So there is a highway,
uh,
and you can have like long distance routers that are directly connected through optical fiber, or maybe like some pointing antenna like LoRa or something. And a big, if you there is a highway, mostly the network will be like a string, right?
like in a for the long range communications, they will be by the end they go to the user. They will again become
User means what? So when you are assuming that there is a highway communication network, for example, and maybe you are accessing internet, right?
uh,
So now when we are speaking about source and destination, we are speaking about the originating router from where the requests have been generated. And
okay.
destination is the destination router, not the user.
Okay,
So
routers.
when we are creating the network, it is always between the router, not the client or the user. So the user who is originating a call, it is going to the nearest router, right?
Okay, got it.
Yeah. So then that router will be the source node. So when we are speaking about source node and destination node, we are not including the user at the source side or the user at the destination side, because it will be anyway, it is one hop, right? That's why it is called last mile problem. In wireless networks, in most of the like underlying networks is mostly connected through optical fiber, most of the cases, right? Or maybe directed
Right.
microwave link. Only the problem of this wireless regime is the last mile problem. So the last base station or the last customer premises equipment to the user. That is always one hop. Is there any question? Like any doubt on that?
That's it. Thank you.
Okay. So with this, let us start this link addition that already we talked about, right? So we'll be seeing that how a network can be evolved to a different kind of network topology when we'll be adding a link, because once we'll add a single, even one long range link or LL, the string topology will never be a string, right? So it will be gradually evolving. Now to what, we don't know. So that's why we are taking two kind of approach, either based on random decision or greedy. So here just we discuss this APL because it is one of the key network characteristics what we have taken as one of the characteristics which will be optimized greedily to get our like overall objective. So when we will be discussing this random decision based link addition, that can be done in two ways. So whether it has been covered in the class already?
random link addition I mentioned, I discussed in class, but you can very briefly touch upon that. That's
Okay. So in random decision based link addition, they can be done in two ways. Either based on pure random decision, means like randomly you will pick, maybe you are tossing a coin. You are getting a probability. If his probability is greater than P, that second one, like new link creation based on probability P. One is like based on pure random decision. You will pick one node A, another node B. If they are not already connected, just connect one. That is the pure random decision. The next one, the new link creation probability, maybe you are like tossing a coin, unbiased coin, and if it is head, you will add. If it is tail, you will not add. Or maybe you are generating a number between 0 and 1. If it is, say, for example, more than 0.3, you will add a link. If it is less than 0.3, sorry, if it is less than 0.3, you will add a link. And if it is more than 0.3, you will not add a link. So it is like new link creation based on probability P. So there are two options. So here we are just showing with pure random decision what we are doing here. So if you'll see this 1, 2, 3, 4, 5. So line 1, we are running for 1 to K as we are connecting K LLs. So line 2, what it is telling that it will be connected between node U and node V if it is not already connected. So E is the already existing links in the network. Because if you'll see at the top, it is required G equal to VE. So V is number of node and E is existing link between the nodes and the network is connected. So if the identified node, two nodes U and V are not already been connected, then we'll add this random LL. Otherwise we'll not add. And if it is done, then we'll add this UV, the link to to E. So for example, when we will go for the second link addition and we will again pick up a random node U and random node V, then we'll check whether it is already connected or not. Then the connected link for the first time, it is already added with E in line 4. So it will show that, OK, the U and V already connected. So pick up another. So you will choose another pair. And like that, you will be adding K links. So time complexity is very simple, like order of K. Because each time you are maybe tossing a coin and identifying two nodes. So for K long links, it is taking only order of K to add K long links. Is there any question? Here we have seen, like we are showing a simple 40 node string topology where we have added 6 LLs based on pure random decision. So there we can see here APL, as already we have discussed, and HND is the highest neighbor degree. So here we can see even if number of links are being added, the highest neighbor degree is not going beyond 3, or maybe if you will add more and more, it will be very slowly. It is approaching the like HND will be gradually getting higher and higher. So HND means like the node with maximum number of connectivity. So for example, if you will see node 1, so it has only 3 links. One between 1 and 2, one between 1 and 27, another between 1 and 22. Like that, we have identified that how many connections are there for each of the nodes. So here we have seen even if we have added 6 links, the highest neighbor degree is never going very high, like 6 or 5, something like that. It's not going like that. So when we are plotting the degree distribution, it is like semi-log scale. You can see x-axis is in logarithm and y is simple. So here we have seen it is like showing bell-shaped curve. and asymptotic value of APL almost like order of log n. So for large size network, when we are adding almost like n by 2 LLs. So for 50 node, we are adding almost 25 LLs. So average APL value after addition of 25 LLs, it is following almost like order of log n. So if it's not like log 50 for 50 node network. But whereas when we will be using this greedy decision based link addition, we can add an LL or maybe KLLs based on greedily optimizing the average path length value. So here greediness involved in optimizing the average path length of a network when we are adding a link. Now there is these two methods. One is like optimal decision based link addition. Another is near optimal decision based link addition. So what is the difference between these two? So let us see the algorithm, then it will be clear. So this is the greedy optimal link addition algorithm where we are adding KLLs all together that will minimize the average path length value in a graph. So for example, if you want to add, like for example, 2 LLs, you have NC2 combinations where you can add those 2 LLs. And for that, each of the cases, you need to identify the shortest path. So for example, if you are running Dijkstra or other Bellman-Ford, any shortest path algorithm, the average time complexity is order of n square log n for n node network. So for adding 2 LLs, it will take NC2 multiplied by n square log n. This is the time complexity just to add 2 LLs. Now just think if n, the size of the network is 1000, what will happen? So if it is like K node network, it is almost like order of n to the power 2k. Yeah, please.
Sir, actually, can you change the admin privileges, sir? Like some of the students are getting removed by someone, sir, like continuously.
Can you just repeat? I did not understand.
You know, Shubham, I have just now converted most students as attendees so that this will not happen. Okay, so
sir, like
can you just check now?
Times.
Yeah, okay, fine. Yeah, I have done that. Okay, no problem. Abhishek, please continue.
So any question? Okay, so here what I was telling, the time complexity, just look at the time complexity for n node network where we are adding only KLLs. So for example, just take 1 LL. If it is one long link, it is like n to the power 4 log n, right? If it is not, if it is like 2 LLs, then it is like NC2. That means n factorial, 2 factorial and n minus 2 factorial multiplied by n square log n to add 2 LLs. So if you will take the upper bound, it is almost like n to the power 2k plus 2 log n to add KLLs. It is very difficult to realize. Maybe this is the best one, this is the optimal exhaustive search, but this is very difficult when n value is very large. So that's why we are going for near optimal. So what is the difference between optimal and near optimal? So here we just changed, instead of adding all KLLs, like for example 2 LLs together, we are sequentially adding one by one. So if we have to add 2 LLs, we'll first add the first LL, then we'll go for the second LL. So we'll just change, instead of adding 2 LLs together, we are sequentially adding 2 LLs. And if we'll find that there are multiple locations, so I'm just discussing line 5. If we are identifying multiple locations where that particular ith LL can be added, and we are getting the same APL value, after that we have to choose one randomly. So with that, the time complexity has reduced to n to the power 4 log n multiplied by k. So as we discussed, for one LL in optimal addition it is n to the power 4 log n. So now we are using this optimal link addition k times to add KLLs. And as a result of that, what happened? The time complexity from this n to the power 2k plus 2 log n, it has come down to k into n to the power 4 log n. Still it is very high if n value is very high. And when we will be discussing later that a heuristic design, that is the reason that if n value is very large, it is not possible in real world scenario to run this algorithm to identify KLs. It may requires like weeks to get the result. So that's why we need some heuristic which can very fast identify those links and give very suboptimal result near to this near optimal link addition. So if we'll see this particular graph here, also we have added 6 long links. In the previous case, when we discussed about random link addition, we did not talk about average path length because we are just adding a link. We are not trying to greedily optimize the APL value, but this particular case in near optimal link addition, this is the scenario with near optimal link addition. We are adding each of the link where the APL value is getting reduced. So for APL for 40 node, it is almost like 13 point something, like nearly like 14, you can say. So with one link addition, it has come down to 8.41. So now when the second long link has been added, you can check that the second long link is connected to node 32 and other node, but it is attracted to one of the nodes that has been identified by the first long link. So gradually when we went for 2 long links, 3 long links, 4 long links, 5 long links and 6 long links, you can see node 32 attracted all the long links when we are greedily optimizing average path length of this particular network. And this magenta color filled network node, this 32, we named it anchor nodes. So as we spoke previously that why and what is done by anchor node? Anchor node is the group leader which is like trying to attract many links and which will identify like all those other links which will actually reduce the communication distance. So here the hop distance we are telling is average path length. So you can see it is drastically reducing with number of links, and also the highest neighbor degree also is getting very high. So now you can say that okay, after adding of many LLs, it may happen that node 32 will be exhausted. Then what? Then the next anchor node will start attracting the remaining links. And like that, until and unless the entire network will be fully connected. So any node can be reached by any node directly. If you will run the algorithm that we discussed here, it will continue. And you will see that first it is 32, maybe then node 8 will come, then maybe some other node will come, and gradually if you'll run until the entire network is connected, you will find multiple nodes are attracting many links. So here another any question?
Yes, sir.
Yeah, please.
Here, sir, you said that node 32 will attract the other nodes. Means all the links are being added to 32.
Yes.
I didn't get that why the 32 is like they are adding to 32 only, not to other.
So did you understand that how we have added the first LL in this particular say A? So this first LL has been added to minimize the average path length. So what happened? If you'll see this particular algorithm, what it will do, it will exhaustively search all possible node connectivities where a link can be added, and then it will calculate the average path length after addition of that particular link, and then it will remove that link, then add the next one. So like that, it will go for exhaustive search, and after that, which link addition will give you the least value of APL, you will keep that link intact, then go for the second link addition. So we just implemented the same thing for this 40 node network. So first link has been added between 8 and 32, right?
Yes, sir.
So and it gave like least value of APL among all other long link addition possibility. So we kept node 8 and node 32 connected. Now they are like directly can be reached in one hop. And then we go for the next link addition. And surprisingly, we have seen that the second link is also attracted to this node 32 and another node in the network. So we did nothing. We did not ask the like other links to be added, or did not give in the algorithm that one node should be 32. We just run near optimal algorithm to add 6 long links. And we have seen that surprisingly, all links are connected to 32, which was identified by the first long link. So that was your question or anything else?
Yes, sir. And sir, it is also possible now that all the links will add to 8. Sir, 8 and 32 are symmetric, like they are.
Yeah, correct. But we'll show you. We will gradually show you that why 8 got attracted.
Yes, sir.
So what we did when like the similar question also we had when we saw this particular result, right? So what we did, then we tried to manually add the second long link, like by keeping 8 as the node, because we have seen that 32 is always getting connected. So once the second link is connected to node 8 and some other node, then rest of the links are also attracted towards node 8, right? The thing is that
Yes, sir.
after 6 long link addition, whatever we have got here, APL value 4.14, we have we got the APL value that was more than 1.14 when 8 becomes the first anchor. So when you are keeping 32, like that is naturally getting selected. It's natural selection. We did not like identify 32. It is getting selected naturally. We got like 4.14 as like average path length. But if we will identify node 8, not naturally selected, but like forcefully selected, then rest of the links also connected to like node 8 and some other node. But the APL value is more than 4.14 after addition of 6 LLs. That means if you will identify 8, it will not give you the least value of APL, which you are trying to like greedily optimize. That is actually surprising result. That and we'll like show you in the like remaining slides that why 32 is getting more like attention when we are naturally like a link is getting selected towards 32. Any doubt?
That's a clear, sir.
Okay. So here the first long link when it is connected between node 8 and node 32, you can just check for a 40 node network, for a like fractional location, what is the fractional location of node 8? Can someone tell? For 40 node network, if node, I will select node 8, what is the fractional location? Anyone? So when I am telling about fractional location, that
1 by
means if so, did you understand that when I am like asking about fractional location, actually what I am actually asking? Anyone?
Sir, at what position the node is situated in the
Yeah,
total
in
number
a
of
40 node, yes, you are correct. So what is the fractional location if I am asking for node 8?
8 by 40 means 1 by 5.
It's almost like 0.2, right?
0.2, yeah.
And for 32?
In 32 by 40, 4 by 5,
0.8,
0.8.
right? So the surprise was that when we took multiple sized string topology, say 10 node, 20 node, 30 node, 40 node, 50 node, 200 nodes, always we saw the first long link is always connected between this 0.2 and 0.8 fractional location. We previously thought we did some mistake in our code. While like writing the algorithm, we did some mistake. But then we understood, okay, no, for each of the cases, irrespective of the size of the string topology, always the first link is connected between 0.2 and 0.8 fractional locations of a network. So for 40 node, it is point like 8 and 32. So what will happen for 30 node? If it is like 30 node network, then where the first LL will be added?
So 6
Yeah, and
24.
right. So for 100, it is like 20 and 80. So just multiply the number of node with fractional location. So for like 50, it is 50 into 0.2, that means node 10, and 50 into 0.8, that is node 40. So the first long link will be connected between node like 10 and 40. And this is actually surprising result. So we call these two nodes as anchor nodes. So the following results when we have seen, so when you are adding like n by 2, the same number of the same experiment that we did previously, we added n by 2 LLs, long links for each of the cases. So for 50 node, we have added 25 long links, and we have seen it is showing a power law distribution. So power law distribution means it is like if D is the distribution of this particular graph. So it is similar to like d to the power minus gamma, where gamma value is 1.8. So here, do you know what is degree distribution? Degree distribution is like how many nodes is having degree k. So this is the plot of that. So here you can see, if you will see the graph, maybe one node, blue means 20. So one node, maybe there are other also, it is very small. So for example, it is 20 node is blue, almost like there are like 10 links with only one node. You understood that? Any doubt on that degree distribution?
Sir,
So
can you
degree
repeat it?
distribution. Yeah, so degree distribution is the plot of how many nodes are having degree D. Here we have plotted this, where x-axis we have taken in log scale. That's why it is called semi-log graph. And the y-axis is normalized. So here you can see 10 to the power 0 means one link. 10 to the power 1 means one, like 10 links. So here maybe like one node is having almost 10 like total links. So HND, highest neighbor degree, only one node. But here you can see very many nodes are having almost degree 1 or 2, something like that. So only very few nodes, that is the anchor node, which attracts most of the links in the network. So that's why you can see very like small spike at distance between 10 to the power 1 and 10 to the power 2. So all are like maybe 10, 20, 30, 40 and 50, all that anchor node, and mostly like 0.8 n node. That has only maybe one node is having that degree. Is it clear?
Yes, sir.
And the asymptotic value of APL is almost like log n. So previously we have seen when we are adding the link with random decision, it is only log n. It is log n. So it is far below. So for 50 node case, it is like log of log 50. So here we have seen that greed is one of the reasons for such evolution of real world skill free network. So this graph is like this degree distribution of power law is one of the key characteristics of skill free network. Whether like skill free network is covered in the class?
No, not yet, not yet.
Oh, so like you will see that in detail. So I'm just skipping it then. And when we are adding LLs with some greedy decision, in this case, we have taken like average path length. You can take anything. So for average path length, we have seen that gradually the first link is added between this 0.2n and 0.8n node. And slowly the remaining links are getting attracted towards 0.8n, and maybe after that it will go to the next like possible anchor node is 0.2. Maybe after that it will go to something when all the links already will be added. And it is based on long range link affinity LRA for unconstant link addition, where we have talked about unconstant because here we did not give anything. Okay, the length of the link will not be more than X meter or X feet. Because when we will take care of like when we will be using some wired network, it can go up to like 100 kilometer. But if you will go for some directional antenna like LoRa or something like that, it may not go more than like 100 meter or something in like dense urban setting. So then the length will also start playing. So until now, whatever we have discussed, we did not take that constant into account. So it is unconstant LL. So there is no constraint on the maximum length. So here we have seen the first LL always connecting between 0.2 and 0.8n fractional locations, and those are called anchor nodes. So now, how much time I have? Okay, half an hour. So now here we'll be describing in brief how we can realize the location of this anchor node mathematically. So for this, what we did, we took a unit length string and number of nodes in that string we assumed it is infinity. So when in unit length string, when there will be infinity number of nodes, it is very dense and we can assume it is a continuous line. So that will not actually affect our like analytical derivation. It will actually help us, because when you will be going to analytically derive something, you need to assume some like bound. Otherwise you cannot, like if you will get the real world setting, you cannot use the mathematical model to derive. So for that we have identified, okay, maybe it is like unit length string and n tends to infinity, and so that we can use this string as a continuum, so that easily we can use this integration into account. Otherwise it will be very difficult to derive. So we'll see in the next few slides. I'll just go very fast so you can like look through the paper and book in that case. So here what we are actually doing, let me just explain. We have taken a unit length string where we are assuming maybe this P1 and P2, if you'll see the, just follow the graph. So we are assuming maybe P1 and P2 being the optimal point or anchor nodes where the first link is added. So here we are trying to identify analytically what is the optimal location of these two nodes or 2 points, P1 and P2. And here S is the source, D is the destination. So when we are calculating APL, what we are doing? We are going from a node, we are counting number of hops or number of path distance. Then we are adding all possible source destination pair that we have already shown in that APL calculation. The same thing. So S can be here as the source, D can be destination. So we'll integrate over 0 to 1 for source. So if you see equation 1, the first outside integral is showing the location of source from 0 to 1. So from anywhere to anywhere source can go, and destination is X unit apart. So we have just use the change of variable. So it will help us to calculate and estimate the PSX value. So here just we did the change of variable. Instead of like D, we use X. So D equal to what?
Destination.
Yeah, no. D equal to destination, but we just change D to X. So we can use like 1 minus X. Or maybe like S plus X is the D. So here X is fixed, S is variable. So instead of using two different variables, S and D, that is source and destination, where both are varying, we just use X as like change of variable and use only one like changing variable as X, S. So we just remove D by using like S plus X equal to D. So here you can see the inner integral in equation 1 is until X equal to 0 to 1 minus S. Is it clear? The limit of two integrals? Any question on this two limit
Yes.
of integral? And we need to identify PSX. So PSX what? PSX is the shortest path. So when we are talking about APL, actually we are taking average over that. So when we are seeing the if you can remember the previous equation here, just I am going back for a while here. So here if you see APL, the outside of the summation is n into n minus 1. So all are like constant. So that will not affect this summation of dij. So if we can optimize the value of dij, obviously the APL value also will be optimized because outside of summation is constant. So in this particular case, what we did not include this APL. We just trying to optimize the path length, overall path length for all possible source destination location. And we also assume that if P1 and P2 be the optimal value, optimal point to add a link, then what will be the scenarios? So here we can find if we assume that P1 and P2 be the anchor points. So actually we segregated this particular string into three parts. One is between 0 and P1, another is P1 and P2, the rest is P1 and 1, right? And as there are three segments of the string, so source can be in any of these three segments. And also we assumed destination is always at the right side just to have a like easier way to estimate. If you will see that OK, D is also the left side, then only the equation will get complicated. That's all. No more than that. So here we assume that D is always at the right side of S, not the left side. It may be left side, but here we assume that D is always at the right side. S is varying from 0 to 1. So actually S is situating between these three segments, 0 to P1 or P1 to P2 and P2 to P1. And based on that, D's location will vary. So when S, for example, if it is between 0 and P1, then D's location also can be in these three segments, 0 to P1, P1 to P2, P2 to P1. But if S will go between the third segment, that is P2 to 1, then D cannot be between 0 to P1 or P1 to P2 as per our assumption. It is just for simplifying the calculation, that's all. So when it is case 1, I am not going into details. You can read, and if you have any like doubt on the like derivation, you can anytime ask me or send me email, I will clarify. So here also what we did, if you will see this highlighted part, so here we are telling the same thing that whatever I told just sometimes back. So when S is between 0 and P1, then D's location can be three part. Either it is 0 and P1, that is the first highlighter. The second highlighter is telling that D is between P1 and P2. And the third highlighter is telling D is between 1 and P2. Is it clear? Any
Yes,
question?
Yes, sir.
OK, so now the thing is that, see, when the first part, so I am just I'll just describe case 1. Other two cases, just it is same thing. Just you need to calculate and see how it is like being evaluated. So I'm just like showing you case 1. So when S plus X is less than P1, that means like D value, D is between 0 and P1. So obviously we will not use this LL, right, between P1 and P2. That's why the shortest path is always X. Is it clear? The first one, it is.
Yes,
Is
sir.
it clear? So now go to the second one. When D is in between P1 and P2. So there are two options. Either you can go directly S to P1, then D, or you can use S to P1, then P1 to P2, then come back to D. And out of these two ways, which one is the shortest, you will use that. So we just mention the same thing here. So PSS is minimum of these two things, the first one or the second one, right? If you will see, you will understand that how we have calculated this S to D and using this long link. The third one also is very straightforward. What? If D is between P2 and 1, obviously you will not use the usual way that S to P1, then P2, then D. You will use this long link. S to P1, then P1 to P2 through long link, and then D. So there is no options there, right? Is it clear?
Yes, sir. And sir, length of long link is 0, no? Like
it is like a unity. Yeah, the same 1 by n. If it is like it is like n node network, 1 by n you can assume, and that will not have any effect on the actual like derivation.
okay, sir.
So any question on these three options? Because if you can understand, then other two cases are also similar. Just you need to check that how it has been calculated. So now we have seen when S is between 0 and P1, and with respect to that there are three segments for D, and we have got this three like minimum value. Now we need to identify for the first part. So it's 0 to P1. That's why instead of like if you'll see this 0 to 1, now it is three segmented 0 to P1. So now we are integrating outside from 0 to P1, and S value is from 0 to 1 minus S. Now we have added all those options here. So that will give us the first case. Similarly, likewise the second case. When S is between P1 and P2, there are two options. D can be between P1 and P2 and 1. Like that we have given two options, and the same thing you can see the outside in equation 3, the outside integral is between P1 and P2, and for 0 to 1 minus S we have integrate the second segment. Likewise, the third segment, when S is right side, it is very simple. There is only x dx ds, nothing else, because it cannot use anything. It will be always at the right side. So now we have three segments, S1, S2, and S3. We added all those three segments to get the actual PSX value. And this is the equation. And we need to minimize this equation to get the value of P1 and P2. And where also we have identified P1 is less than P2, that means nothing, that in this particular equation will not change the location of P1 and P2. So here P1 is near to 0 and P2 is near to 1. That means always P2 is always greater than P1. Just we mentioned that. Is it clear?
Yes, sir.
Yes, sir. So actually this function is strictly convex, and we found when we solved it, the P1 and P2 value is 0.2071, 0.7929. It's almost like 0.2 and 0.8. That also we found during our observation in like near optimal link addition algorithm implementation. So we here analytically prove that yes, the first link is optimal and it is connected between this anchor node P1 and P2, which is fractional locations of 0.2 and 0.8. Now the question is why? As you like someone of you asked me, why not 0.2, why 0.8? So here comes the situation. So if you have a circular topology and if you want to add a link, long link, which will greedily optimize APL, you will always find it will connect between 0.25 and 0.75 n. So like 100 node case, it is between node 25 and node 75. Now, if you will just remove one link, say for example, here we have shown node 1 and node n and removed one link. So actually it has now become a string topology. And surprisingly, we have seen the long link location from this 0.25 n, it shifted to 0.2 n, and 0.75 n, it has shifted to 0.8 n. Now, why such shifting has happened? So when we try to identify that why such shifting, any reason behind that? So we found if we'll see the path length segments between 1 to 0.2, then 0.2 to 0.8 and 0.8 to 0.n, and how much like fractional location for each of the fractional location, how much they are contributing to generate the total path length. We have seen that when it is between 0.2 and 0.8n, it is generating like almost like double the size of the point, like between like 0.1 to 0.2n and 0.8n to 0.n. So did you understand this particular table? Any question on that? So here when I am telling that for node 20, serial number 1, it is like path length between 1 to 0.2n. So for 20, it is like 1 and 4. Almost like 660 is total contributed from that particular segment. Now from node 4 to node 16, almost double than 660 has been contributed. When you are actually calculating total path length, and then you will be like going for adding all those 3 segments and then like divide it by n into n minus 1 by 2 or directly n into n minus 1. Then you will get the APL value. So it is actually contributing double. And as a result of that, it has shifted its location from this 0.25 to 0.2 and 0.75 to 0.8n. And it has more inclination towards 0.8 as a, like one of the reason is that like it is always like going to the higher side of the network. Like still we don't know why, but it is always going to the higher side whenever we have seen. So if you have a network, when you are like identify a network like node 1 and node n, it will always have inclination towards node n. Just reverse the numbering, it will also reverse the location. So one like example application of anchor nodes. So where we want to show you that one simple heuristic design. It's called SDLA, sequential deterministic long link addition strategy. What it is actually doing, as we have seen from our like earlier experiments and analytical derivation, that the first link is always added between node 0.2 and 0.8n. So we are like blindly adding the first LL between 0.6, like 0.2 and 0.8n. So here in this 30 node case, we have added between 6 and node 24, the first link. Now, as a result of that, there is now 3 segments. We are telling it as span distance. So we are counting the distance. So it is like 5 hop. The next one is 18 hop. And the next one is again like 6 hops. Now, whichever has the highest value. So here the in between the segment has the highest value 18. So what we are doing? We are taking 0.8n as the anchor node and divide the highest span distance divided by 2 and add a link to that. So likewise, when you will be adding the next one, now you have 4 segments, 1 to 6, 6 to 15, 15 to 24, 24 to 30. Now you need to calculate the span distance. Here still it is 6 to 15 is 9, 15 to 24 is again 9. So one of the segments, both are same. So you can take either from the first or from the last, it is your wish. Then you will have 24 as one of the link and the span, whatever you will be taking like 6 and 15 or 15 and 24, just add a link between the middle of the node. So for example, 6 and 15, so 11 will be the middle of the node. So the next link will be added between 24 and 11. Understood? And for this particular heuristic, it will take only order of k times n to add only KLLs, whereas for near optimal link addition, it was like almost like k into n to the power 4 log n. So it is like too fast. Like in minutes you will get k long links case. So the next question will come. Okay, by this algorithm we have added k links, but what is the performance benefit? How much it is deviated from the near optimal case? That is obviously the question. So we'll go to that question. So here just we have shown that for 6 link addition in 30 node case, this is the first one is based on near optimal and the second one is based on SDLA. So what is the performance deviation? If we'll see that the performance deviation is maximum 6.33% for 50 node case. We have simulated from 20 to 100 and we have added almost like n by 2 LLs. So percentage deviation is highest only 6.33, whereas the difference is very minimal, maybe like less than like 0.5% between SDLA and near optimal. This is this much close, and like application wise it's much faster. It's only k by k times n for k LL addition, and that is like k times into the power 4 log n for k LL addition with near optimal. So actually SDLA is performing better and it can be used in many real world applications, like whatever we have discussed previously. Like in such cases, we can easily deploy SDLA based link addition and add those link, and almost the APL optimization performance will be very high. So at last, you open research areas. So in 2-dimensional network, whether any anchor node exists, if it exists, where it is, still it is an open question. So another is how to add links in ad hoc or tactical networks, because when we will use ad hoc and tactical networks and when wireless scenario will come into picture, then we need to assume many more things, not only this link addition. So when we mentioned about unconstant LL, so then there will be constant LL because of the limitation of the wireless environment. So that will be very interesting. Then robust and ubiquitous community broadband networks design. Then fault tolerant next generation networking design, and also like the current one is IoT, fog computing, SDN architectures, M2M deployment, industry 4.0, 5.0, whatever you will ask for. So it requires your like data packets to be delivered to the data center very fast. So how it can be done? So you can easily minimize the APL. Then how to minimize the APL of a random network? It is an open question, because if you have like 1000 node random network, it is like very difficult to exhaustively search, because already we have shown it is like into the power 4 log n. And with time, the requirement will change, and in real world setting, it is very difficult to give such long time to just identify where to add. Because if it is like a fixed allocation, then maybe we can incur that much cost. But if it is like real world and instantly, like for example, it is like military communication network or disaster response network. So you need to identify the nodes very fast, maybe in minutes. Then what you will do? So that will be very like challenging questions that can be answered by identifying these anchor nodes. So whatever we have covered, it is mostly you can find in this book. I hope you have access to the chapters and the content. And that is all from my side today. If you have any question, please ask. Thank you.
Sir, SDLA will only work for this linear type, right?
So yes, so when you will be developing a heuristic is always by looking at the exhaustive search, right? Or anything that is very complicated, maybe optimization design. So heuristic is always looking at the trend, and based on the trend, it will mimic some of the trend and then intelligently use some other characteristics. So here in this case, for particular, here we have used the span distance. That is the value addition, because the first link we have seen from the exhaustive search. So if you want to use SDLA for some other network, obviously first you need to check how the network is being designed, because when you will be like developing some heuristic, for example, you need to give this kind of performance evaluation test, right? Am I correct?
Yes, sir.
So anyway, you need to run this exhaustive search or maybe optimization, anything. So any heuristic design, not only SDLA, anything. So heuristic design is always very specific to a particular topology or particular setting. Because whenever you are designing some heuristic, you are giving, first you are giving an example scenario and how the optimization has been implemented on that particular setting. And as the optimization is always very hard to achieve, or sometimes it is NP hard, you cannot even achieve, then you are designing heuristic based on some of the outcomes that you have seen for very small size network that is not possible in real world setting, and then mimicking some of the key criteria while designing the heuristic. So obviously, yes, as per your question, SDLA cannot be applied to any other network than string topology. If you want to use SDLA, first you need to adjust SDLA as per the requirement of that particular topology.
Okay, sir. Sir, if we are having a random network, first we will find heuristics for a very small network of such kind.
No, then
and then
your steps will be as follows. If you have a random network, first you need to run. So first you need to identify actually what you want to do. That is the first step. So for example, you want to minimize the APL. So now you have identified one of the network characteristics that you want to minimize, right?
Okay,
now the
sir.
third step, you need to apply some greedy algorithm, or you need to have an optimization framework that you need to solve through optimizer. There are lot of optimizer are present, there are IBM Cplex, then Python Gurobi, then even MATLAB you can solve optimization if you have some optimization framework to be analyzed and designed. And then by seeing that, you need to identify the heuristic model. So these are the steps for any kind of network or any kind of performance. Whenever you want to design heuristic, that is the steps you need to follow.
Okay, sir. Sir, if the network is very random, we can't even only when we run. We have to run it for weeks then for a bigger network to even understand it.
The random network is always challenging, very challenging.
So then finding
So
heuristic
recently,
is
maybe 2 years back, we published a paper where we showed a random M2M network deployment in a industry 4.0 environment. And there we proposed a heuristic called clause. So that will identify the long link location, and we actually performed constant LL addition. So there, because the link additions are based on wireless networks. So random is always very tricky.
okay. Thank you.
Sir,
Yeah, please.
so for 40 node network, you told that the 8 and 32s are the anchor nodes. Both are anchor nodes, or 32 only is the anchor node?
No, so actually, let me explain one more time. So here we are telling the node 8 and node 32, both are anchor nodes. So here you are seeing only 6 link addition, right?
Yes, sir.
So in a network, there will be multiple anchors. So we found 2 anchors in a string topology by adding the first LL. So when maybe 32 will be almost added to all other nodes in the network, then maybe node 8 will start picking up the links. naturally, if you are not forcing it to adapt. As I told previously, if I will force node 8 to add the second link, maybe third link onwards, node 8 will pick up all the links. So both are anchor, but 32, when you are connected to 32, you are getting lesser APL value than if you will use node 8 as the anchor node. That's why maybe 32 has been picked up as the anchor node, but both are anchor node.
Okay.
And sir, after this, say this addition of second link also, then here 8, 20, and 32, all three are anchor node. Huh?
No. So here, that's what I'm telling. See, we don't know that next which anchor node will appear. So what we found, the first link is always optimal. It has a clear-cut identity of connection. So for any size of network, it is always like 0.2 and 0.8n, right? Now these two are anchor nodes. Now, as per your question, whether 20 will become anchors, it may. When 32 and 8 will be over, or maybe almost like connected to all other nodes in the network. So say for example, if you have n node network, so for a fully connected n node networks, how many links should be there?
So n minus 1 by 2.
Right. So it is like n square minus n by 2. Here, how so for 40 node, what will be the total number of links?
14 by
The
2,
40 into
7.
39
91
by 2. So like 20 into 39. So more or less 780 links. Right?
Yes, sir.
So as of now, how many links are there? Only 39. First link, only 40. Second link, only 41. So 6 links, only 30, like 45 links are there in a 40 node network, and 780 links are required to make it fully connected. If it is like bidirectional, if it is directional, then it is like double than 780, double of like 780 into 2. So this many links will be connected, then the network will become fully connected. So obviously there will be multiple anchor that will be evolving. But in practical scenario, just think, like for example, how many servers Google have across the world? I think 5 or 6, right? We may not know the location, but it is almost like 5 or 6 servers which is serving the globe, right? So you may not require many anchors or many hub to serve the purpose. If you want to go for like all connected, then at the end, like nothing will remain. All node will be connected to all other node. But that is not the question, right? We are trying to optimize the existing sparse network with the help of very few link addition. Because for each link addition, for example, just think when we are talking about anchor node in this particular 40 node network, then node 8 and node 32 are becoming anchor node. So to connect multiple links between 32 and other nodes, if I am only adding, say, for example, 6 or 10, maybe then all links will be connected to 32. Then how many ports are actually required when you will be mimicking this particular topology in real world? So either you need a switch if you are using some wired connectivity, if you are using wireless connectivity, then you can understand you need that many directional antenna to be supported by node 32. How much energy will be dissipated from node 32? You need to like minimize that part also, right? Nowadays everything is green, so you need to reduce the carbon emission. So in real world setting, you may not have like flexibility to add like 50 links or 60 links. Maybe you may maximum add 10 links, 20 links. The question is where to add and how to add based on your requirements. So here we have shown just to minimize APL where link has no constraint, all are unconstrained link addition. Now you just start putting on constraint on links. If it is like wireless, it cannot go beyond X meter, then the entire topology will start changing. So there will be new problem you can deal with that.
Yes, sir. And sir, one more question. You said that the finding the anchor point in the 2D network is still a research problem.
Yes.
And so like anchor point is that we have to just find that how we can reduce the APL. Then by using the justices also we can do the in the same 2D also. Then why it's like
correct. You are correct. But the thing is that see the time complexity. So now if you have 100 by 100 2D network. So to add even 5 LL, what will be the time complexity? 100 to the power 4 log 100. Is it possible actual, like in actual deployment, like for like experimental purpose, obviously, yes, you need to run, otherwise you cannot compare. That is different case. But now I want to add 3 LLs in a like grid kind of topology. I need to add within 1 hour time. Maybe today is the time when I need to add maybe 3 LLs. I have only 1 day left to identify the locations. Now, whether you will run this greedy algorithm to find those 3 locations for a like 100 node, 100 by 100 grid network, I don't think so.
okay, sir.
So it may take maybe 1 week. By that time, your contract is gone.
Yes, sir. So like we have to find some heuristics so we can reduce this time complexity.
Yeah,
in
so
the 2D.
the main aim of designing any heuristic, not only for this, anything. The heuristic design is to address the main issue of time complexity reduction and giving a comparable performance over the existing methods like either grid decision or maybe optimization framework or like exhaustive search, whatever you talk about or take. It should give a comparable performance so that performance should not be like deviated like 20% deviation. No one will approve your heuristic. It should be very less. That's why we can see here, right? So here only 6.33%. So plus minus 5 to 10% is okay. Because maybe you may also say why it is 6.33, it may go down to 5, but here you can see it is not only 6.33%, we have also reduced the time complexity from n to the power 4 log n to only n to the only n. So we have from non-linear time complexity to linear time complexity easily can be achieved. So that easiness of achieving this link addition gave us this leverage of going above 5%. Otherwise, anyone can ask, okay, why not below 5%? So that is the leverage. You need to like trade off, right?
Yes, sir.